Hi, my name is Desiderio Kovar, and today I'd like to talk a little bit about some of the research taking place in my group. I have two major thrusts taking place in my group related to additive manufacturing that really are at opposite ends of the spectrum in terms of the size scales of the parts they produce. The first thrust is aimed at producing microscale parts, and the second thrust is aimed at producing large parts made out of ceramics. Let me start by explaining the first process, which is aimed at producing microscale devices made out of ceramics and metals. The way this process works is we start with a powder of either the ceramic or metal that we wish to deposit, and we feed that powder out of the feeder and into a mixer, which shears the powder and breaks any agglomerates that might be present in the powder. That powder is then aerosolized, and all of this takes place at about atmospheric pressure until this aerosol of particles and gas make their way through the nozzle. The nozzle separates two parts of our machine. The upper part of our machine is at about atmospheric pressure, and the lower part, the deposition chamber, is pumped by a vacuum system. So there's a large pressure differential between these two regions. And that actually causes the gas that is part of the aerosol to accelerate. And because the particles are entrained within the gas, they also are accelerated by the drag forces that act on the particles. And our typical particle velocities when the particles come out of the nozzle are anywhere from a few hundred meters a second up to about 1,400 meters a second. And we can control that by controlling the nozzle geometry, the gas type, and the gas temperature. When the particles impact at these kinds of velocities, they're moving fast enough that they actually plastically deform where they hit the substrate and they stick, and we build up a film. And we do this all at room temperature. And so we can actually directly write at room temperature metals and ceramics into pattern thick films. And these are some examples of the types of films that we routinely make in our lab. You can see we can deposit on a range of different materials. So the substrates can be made out of plastic, they can be made out of metal or ceramic. The second thrust in our group is aimed at solving a very difficult and challenging problem for additive manufacturing, which is trying to make bulk ceramic parts. There are a number of processes that are very capable of making small ceramic parts or parts that have a thin wall. But in terms of processes that can make bulk ceramics, large ceramic objects that have a thick wall or are solid, that's a really challenging problem right now. So we've been working on a process called selective laser flash sintering. The way this process works is it utilizes a combination of a large electric field of order about 1,000 volts per centimeter with a localized heat source, and in our case we use a laser, to locally sinter the ceramic material wherever the laser beam passes on top of the ceramic powder bed. The very large electric field, it turns out, has some very significant consequences. It significantly reduces the temperature required to sinter ceramics, and it also significantly increases the rate at which that sintering happens. So rather than the typical sintering times that we are used to with ceramics of many, many hours at very, very high temperatures, for example, for aluminum oxide, that temperature can be 1,500 or 1,600 degrees. With the presence of the electric field, we can bring that sintering temperature down, the sintering times down, so that you can actually get sintering while the laser is scanning. Selective laser flash sintering is a process that was discovered in our laboratories only a few years ago. Right now, we're actively doing research to try to understand the fundamentals of the process with the goal of turning it into an additive manufacturing process. If you're interested in talking further about either of the thrusts that I've mentioned in this video, please contact me and we can talk more. Thank you.